x squared plus 9/4 cubed dx. All right. Now it looks like that one, right? We have x squared plus a constant. So we're going to go and use our trig sub now. So I'm looking at, so this is where I'm going to do my trig sub over here. I have the square root of x squared plus 9/4, which means that a is what for us here? We haven't had an a like this before. 3/2. Right? This is a squared, right? So you're taking the square root of that. You get 3/2. And what's the substitution I make? 3/2 tangent theta is the trig sub. The square root of x squared plus 9/4, right, is going to be equal to 3/2 secant theta, because we know this. And then dx, we can get from this, is 3/2 secant, not tangent, secant squared theta. Okay. And now we get to rewrite it all, right? Okay. Here we go. This integral becomes 1/8 integral x cubed on top, right? Okay, that's x, so I'm going to cube it. 27/8. I'm cubing this and then cubing that, so 27/8 tangent theta to the third, tangent cube theta, sorry, over the root thingy, right? The root thingy is this, right? Cubed, though. Cubed. So it's this cubed, which again is 27/8, but this time secant cubed theta. And then times, don't forget dx. dx is 3/2 secant squared theta d theta. 3/2 secant squared theta d theta. 27/8 cancel, that's nice. 3/2 will go out. I can also cancel out these two factors of secant, and that leaves me with just one factor of secant in the bottom. Three 3/16 is what's on the outside now, because I pulled out a 3/2. What do I have up in the numerator? Tangent cube theta. Denominator? Just secant theta. Just secant. And that's it. Again, our tangents and secants are in the numerator and denominator, respectively. So let me get everything over in terms of sine and cosine again. This won't happen on every problem. Sometimes you'll get tangents and secants and you'll do what you did for your homework last time, where you have to like peel off a secant squared, or you'll peel off a secant tangent and then use what we did, well, in the beginning of this section. Okay, equals 3/16. All right, I'm going to have sine cubed theta over cosine cubed theta, that's tangent cubed theta, over what? 1 over cosine? Which really flips a cosine up top. And then one of your cosines cancels, right? Seriously? 3/16 sine cubed theta over cosine squared theta d theta. Now what? Pull out what? One factor of sine. And then let cosine be u. That should work. That should work. Let's see. We have 3/16 integral. So I'm going to take one of these signs and pop it out to the outside, right? Which leaves me with the sine squared on top, right? When I pull this one factor out. So I have a sine squared on top, but I already know I'm going to do what with that? Change it to 1 minus cosine squared. And then what's on the bottom? Cosine squared? Y'all know what I did there? Right? Pulled one sine out, left a sine squared. I rewrote sine squared as 1 minus cosine squared. Okay, now what? You want to do u as cosine? Du is negative sine, but I'll just go ahead and make that negative du. Oh, man. Equals 3/16 integral 1 minus u squared over u squared du, and that should have been a negative du, right? So why don't we just put the negative out here? So don't forget that negative du there. What are you going to do with that? Split it up. Two integrals. Because you have a single term on the bottom, two terms on the top. Split it into two different fractions. So this becomes negative 3/16 integral 1 over u squared, right? Which is u to the negative 2. And then minus u squared over u squared, which is 1, and then du. And at this stage, we can integrate. What is the antiderivative? Negative 3/16 out here. Antiderivative of u to the negative 2. Negative u to the minus 1. And then the antiderivative of 1, which is u, because u is our variable, plus c. But that's the same as, I'm just getting somewhat annoyed with all these negatives. So that's the same as 3/16 u to the negative 1 plus u, right? Plus c. So I just distributed the negative through because I just don't like all those negative signs. They're bothering me. Is that all right? And then now replace u. So u is cosine. So this is going to be 3/16. And then what's cosine to the negative 1? 1 over cosine, which is secant. And then plus u, now that is cosine theta, so plus c. Now what? Reference triangle, right? Back to x. I told you these problems would be long, right? I told you this section would be somewhat tedious. You can. It's up to you. I don't care. It's just a constant, so. All right, so I go back to my original substitution, which was something like x was 3/2 tan theta, right? That seems kind of weird, but just multiply both sides by 2/3. And you get 2x over 3 is tan theta. Right? That's what would happen if I multiply both sides by 2 and divide by 3. And then my triangle, theta's here. Tangent is opposite over adjacent. And then this side, hey, check it out. 4x squared plus 9. Our good old buddy from the beginning, right? What's up? You sure? Ask.
Because that was the original
Substitution. That was, right? And then I multiply both sides by 2 and divide it by 3. And then triangle tangent is opposite over adjacent, opposite over adjacent. And this side should be the square root of the sum of these two squared. Should go there. So secant is the reciprocal of cosine, and cosine, of course, is adjacent over hypotenuse. So here we go. 3/16 bracket secant off this triangle is the hypotenuse over the adjacent. And then plus cosine, which is the adjacent over the hypotenuse. All right, we're there. You all right with it or no? How are you feeling? It's just a lot of work, right?
Make it look any prettier, find common denominators or anything?
Nah, you could distribute this through. If you distribute that through, 3's cancel, you get 1/16, then times that root. Go here to here, you get 9/16 times that, 1 over that root. At this point, it's just, whatever you feel like you want it to look like. We've got it back to x, right?
So you can stop once you get back to that?
Yeah, I think once we're here, because really at this point everything's just algebraic, but you're not going to come up with a different expression. It's still the function of x that when you take its derivative you get that. We think, right? We hope we didn't make any mistakes. All right, y'all are gonna have fun this weekend, huh? This homework assignment's gonna be really fun.
Lots of fun.
Yeah. Okay. I'm going to try and squeeze 2 more in here. Oh, I know, right? Oh, man. By the way, I was asked to bring the sign-up sheet in case you haven't had a visit with me for that bonus. Anyone want to sign this or no? Okay, you can look at it. Put your name on a time slot. Just, I wouldn't put today. Okay, There's 2 more I want you to see, some things that can come up. Okay, how about this? Just a quick glance at that. No basic U sub, no integration by parts. You have but one option here, and that is trigonometric substitution. Mm-hmm. Okay. You sure? If I had an x out here, right? I'd be happy. Because then derivative of the inside's out there, you're off by constant, but there's no x. Integration by parts. Yeah, the only thing you could choose for u would be the whole root thing, and then the derivative of that's nasty. And then you have to go and, the new integral is the voodoo part, would be an ugly integral. So, yeah. But this looks a lot like square root of a squared minus x squared, right?
Yeah.
Kind of. We don't have a 1 in front of x squared. But we just dealt with that a second ago, right? So what can we factor out here? A 4. So yeah, let's see if we can't do this a little faster. I'm going to pull a 4 out of both of these, right? That 4 is going to get rooted, and it's going to come out as a 2. And that 2 is going to come out of the integral. So that's this. I still have root here. Now you tell me what's under here?
3/4
Yeah, 3/4, 3 over 4
minus x squared.
minus x squared dx. We good? Okay, that part, now we are in this form. So what is the trig sub I'm going to use here? X is a sine theta, right? Oh crap, we never talked about what a was. It's the square root of that, right? Square root of that. Square root of that, right? So you do the root of the top and bottom separately. So a is root 3 over 2. That's what it is. Okay, that's just the way it is. So x is going to be a root 3 over 2 sine theta. The square root of 3/4 minus x squared, automatically we know this turns into root 3 over 2 cosine theta, right? That's the formula. That's what we showed in the very beginning. And we also know that dx is going to be root 3 over 2 cosine theta d theta. This marker's starting to fade out on me here. Nope. Might have to cancel class. Okay, what next? Rewrite? Ooh, that was pretty good. Yes?
So is it always like when you take the derivative of the x and the other side, and then the square root part, what you said equal to, is that always the same as?
No. These are not always the same. Yeah. Yeah. Yeah, so if you make the tangent substitution here, this turns out to be secant and this is secant squared. So these aren't always the same. Depends on the substitution you're making.
Okay.
This dictates what this is going to be. And these two don't always match. Okay, so what does that root of all that stuff turn into? Well, that's right here, right? Root 3 over 2 cosine theta times dx. Root 3 over 2 again. Cosine theta d theta. All right, let's get all of our constants out. We've got root 3 and root 3. They're being multiplied, right? So that's 3. And then on the bottom we've got 4, but then there's a 2 out there, so it reduces. What do we have on the outside here? 3 over 2. 3 over 2 root cosine squared theta d theta. Yeah? Hey, we've seen this. Even power of cosine. So this becomes that formula, power reducing formula, 1/2, 1 plus cosine 2 theta d theta, right? So that's how we take care of cosine to an even. We use that formula from last class, or the formula from pre-cal. Take the 1/2 out, so we've got 3/4 integral. We're trying to integrate 1 plus cosine 2 theta. Hey, that ain't too bad, right? We can integrate that. What's the antiderivative of 1? Theta, right? Because our variable's theta here. So we've actually got a good thing going on here. Let me move this up here. Any questions while I erase here? Yes? What's up?
I kind of got lost right there. Yeah, right there.
Here to here?
Yeah.
Last class, we were talking about powers of cosine that are even. We use the power reducing formula. There's the power reducing formula.
Gotcha. That's what I figured.
Yep. Okay, so I'm going to just erase to there. So we're at 3/4, and then now our antiderivative, which you said was theta, right? And then, what's the antiderivative of cosine 2 theta? 1/2 sine 2 theta, right? Then plus c. Now what? We got to get back to x, right? We got to get back to x. Does anyone notice we have something different in this one than what we've ever had before? We have a 2 theta here, right? not sine theta, it's sine 2 theta. And notice this one isn't even like cosine or tangent or anything like that, it's just theta itself. That's why I'm showing you this problem, because that changes things. So let's go back up to our trig sub, because this is where we created the triangle from, right? Our triangle came off of that right there. Let's just go back up to that real quick. Let's try and create our triangle. So we're going to get 2x over root 3 is sine theta, right? Our right triangle, theta here, opposite over hypotenuse, this is root 3. And that means this side is square root of that squared minus that squared. And again, that should look familiar, right? That was the original piece. If you do this and this doesn't come out to be your original thing, like something has gone bad somewhere in your math, you messed something up. Okay, now, here's the problem that we were running into. We know what sine of theta is, right? But we don't know what sine of 2 theta is. And no, you don't just double that answer. Okay, you just don't go times 2 times 2. You don't do that. Also, we want to know what theta is. Just theta. So let's attack the theta part first. If I want to know what theta is, then all I have to do is take this equation right here and take arc sine on both sides. Arc sine, inverse sine. So if I take the inverse sine of this side and then the inverse sine of the other side, I just get theta, right? And check this out. Theta is actually a function of x, right? This just has x's in it, and that's a function of x. So I'm going to replace theta with arc sine, not 1 over sine, arc sine of 2x over root 3. Okay? So that's taken care of. Now the only thing left is to figure out what to do with this. And does anyone know what I'm going to do with that?
Change it back to sine squared.
Change it back to what?
Sine squared. Oh wait.
So you're thinking of like undoing the yeah, I can't. But there's some way to get that 2 theta to become theta.
Oh, isn't it like 2
Yep.
cosine sine?
2 sine theta cosine theta, yes. That is an identity from pre-cal, and it peeks this little ugly head out here in this class also. That's the double angle identity for sine. So that's one of the big identities in pre-cal. It allows you to take sine of 2 theta and turn it into 2 sine theta cosine theta. And check this out, we had a half in front of it, so half of that 2 is going to go away.
Get rid of it.
So all you're going to have is just sine theta cosine theta. And now you can use your triangle, because that's sine theta cosine theta, not 2 theta anymore. So I think we're there. This is 3/4 bracket arc sine of 2x over root 3 that's theta plus, and then the half and the 2 canceled, so I need to know what sine theta is. Do I know what sine theta is? Off my triangle, it's that over that, so 2x over root 3 times cosine theta, and cosine is adjacent over hypotenuse. So root 3 minus 4x squared over root 3. Close my brackets, add a constant, and I could distribute through, I could put these root 3's together to become a 3, right? I could pass a 3/4 through, but at that point I'm there, right? So I kind of like, I don't know what I'm envisioning here, but there was a comedian that I'm not saying I liked him, but do you remember a comedian named Carrot Top?
Yeah.
Okay, didn't he like always go on stage and have like a bucket of stuff, and he's always like pulling stuff out looking for something? Right, his props, right? I just picture you, now in these problems, I just picture you like, you're looking and you're like, where's that formula? Where's that thing from pre? There it is. Okay, yeah, okay, needed that, right? I mean, just everything's on the table here, right? Everything's on the table, which makes it a little bit messy. One more. I know, you're tired, right? Tired?
Yes.
This is somewhat mentally straining.
Not tired, tired of.
Tired of this?
Yes.
Yeah. Oh. If this turns out to be nasty, we can blame it on the author, because this problem's coming right out of the book. All right. You know, I don't know if this author is still alive. I think he is. James Stewart. I think maybe initially, when you look at this, you should probably be saying, wait a minute, I don't even see a square root in there. Right? Like, I don't see a square root that falls into any of the forms that we've had. Do you agree?
Yeah.
So you start thinking substitution, integration by parts, and yeah, they're not going to work. So yeah, you give up. You go down and change your major. All right. That root that you couldn't see is here, hiding from you. Right? Right? I mean, tell me if I'm wrong. Is that right? Okay. Because that's raising it to the 1/2, then to the 4th. So when you multiply 1/2 times 4, you get 2. Well, that's why I'm showing it to you. And I'm showing this to you because you wouldn't have thought of that. So I have to show this to you so that you start thinking like that. Root x to the 4th power is the same as x to the 1/2 to the 4th, and you multiply 1/2 times 4, that's x squared. So you can rewrite x squared as root x to the 4th. Yes?
So when the first thing you thought was, I can't do use substitution, I can't do integration by parts, so you knew it had to be a trig.
Well, it didn't have to be, but I can make it look like a trig. Okay, so that's what I'm thinking. I can make this look like a trig because I can always rewrite squared as root to the 4th. And then now this, you should be looking at that right now and having a problem. Because that doesn't look like anything we've done. Right? That doesn't factor. This doesn't factor. Even if it did, it wouldn't do anything. So watch, this is important. I have 10 minutes. I don't know how much of this I'm going to get through. We do not have the form x squared minus a squared minus x squared, or x squared plus a squared. We actually have this middle term right here that we have not had before, right? Like if that wasn't there, right? If that was x squared plus 2, then we would have one of the forms. So here's what I'm going to do. I'm going to go back to college algebra. And I'm going to complete the square on that. Sorry. Okay, so what is the method for completing the square? And please pay attention to this, because some of you were taught completing the square in a way that you are going to get yourself into deep trouble here, okay? So let's make sure we're all on the same page on how to complete the square. When you complete the square of a quadratic, you first put it in descending order. Highest power of x down. Next step is you must make sure that you have a coefficient of 1 on x squared, which we do, right? In one of your homework problems, you are not going to have a coefficient of 1. So you'll have to factor it out first. Okay? So here I am. I've got that. I've got a coefficient of 1. I'm ready to go. So what's the next step? What do you do for completing the square? I'll give you a hint. You have to do something with that number. You take half of it. Okay, so I take half of that. -2, I take half of it. Always take half of it. So if that was -3, I'd take half of it. If that was 8, I would take half of it. Okay, so take half of that. When you take half of that, you get -1, right? Okay, now, what do you do with that number? Square it. So you're supposed to take that, square it, and you get 1. So, by the way, this is called completing the square. I'm just going to put complete square. All right, so I get this number 1. Now, what am I supposed to do with this 1? This is where I'm interested to know what you've learned. Plus 1 minus 1? Okay, so some of you have learned completing the square. You get this number, and then you add it to both sides of the equation. Does that sound familiar? Okay, problem is we don't have an equation. We have an expression. You can't add something to both sides if you only have one side. Yes?
I thought we were just adding a 0 to plus 1 minus.
That's what we're going to do. But I'm saying some people have been taught completing the square back in college algebra when you were dealing with equations, and so the teacher gives them a shortcut. Oh, just add that number to both sides. That's fine and dandy in college algebra, but it doesn't fly here because we don't have equations. So the more powerful and correct method is to realize that you've got this, and then you've got this hidden 0. You've got plus 0 right there, and then plus 2. So I've noticed there's a plus 0 right there. And that plus 0, I'm going to rewrite it using that number 1. X squared minus 2x. So I rewrite that 0 as plus 1 minus 1. And then I still have out here plus 2. And the whole reason we do this is because the first 3 terms turn out to be what? Guaranteed. They factor guaranteed, right? These will guarantee factor. This is what we call a perfect square trinomial. So this will become x minus 1, that quantity squared. Always, that'll factor. And then you still have these 2 terms, right? So plus 1. All right. So this is really that, right? That's what we're saying? So let's go back over here. Integral, x squared plus 1 over, here's the square root, and then I have x minus 1 squared plus 1, and then dx. Oh, I forgot to the 4th power. Oh, there we go. Now, does that look like one of the formulas? Kind of, but not really. I mean, like, this is, if this was like x squared plus 1, we'd be in business, right? It's not x squared plus 1, it's x minus 1 squared plus 1, right? So, I'm going to just make a quick substitution. I'm just going to let u be x minus 1. Just a quick one, all right? And let's just see what happens. What's du? Dx, right? Okay, so let's see what happens here. If we rewrite this integral, let's take care of what's down here first. We'll deal with this in a second. The bottom will be square root of what? U squared plus 1, all of that to the 4th power. And then the dx gets replaced with du, and then I have to replace x squared plus 1 with something. All right, well, what's x squared? Shoot, okay, come over here. X equals u plus 1. And that means x squared is u squared plus 2u plus 1. I actually have to square this side and this side, right? So that means if I take this and put it there, I get what? This is x squared, right? So this is u squared plus 2u plus 1, so plus 2. Oh, this is life in Cal 2. All right, we're ready for a trig sub now. Because look, you see it? That's basically x squared plus a squared. But we're using u's now instead of x's. So here we go with the trig sub, and I have 3 minutes. I'm sure we're going to do it. Okay, so here we go. Trig sub. The trig sub that I'm going to use here is not x equals, right? Because I'm not using x, I'm using u right now. So u equals tangent theta, just tangent theta. Why not, what's a? A is 1, right? Because that's a squared. So a is 1. I'm using this substitution because I have x squared plus a squared, right? That's the form I have. All right, I know that the square root of u squared plus 1 is going to turn into automatically secant theta, right? And then I know that du, not dx, du is going to be secant squared theta d theta. Yes. We're there, folks. We're not to the answer, but we're at least to the place I think you could take it from here. Let's see. You ready? All right, let's see what we've got here. I've got u squared. That's tangent squared theta plus 2u, 2 tangent theta, plus 2 over the root thing, right? The root thing is secant theta, right? But it's to the 4th power. So secant to the 4th down here. Cool. And then don't forget du. Secant squared theta d theta. And we get some cancellation here.
Yep. Secant squared is gone.
Secant squared is gone. This 4 becomes a what? 2. And so don't you have these 3 terms over a single term? And so can't you split this into 3 separate integrals? The first integral is going to be tangent squared theta over secant squared theta plus 2, I better put d theta there. That's my first integral. It's that over that. Plus, I'm going to pull the 2 out. I have tangent theta over secant squared theta, d theta. And finally, my last integral is just pull a 2 out. 1 over secant squared, which is cosine squared, isn't it? D theta. All right. I haven't taken the antiderivative, right? So this, I probably turn this to sine and cosines, right? Because isn't this sine squared over cosine squared? And 1 over cosine squared? And when that flips, I believe this is going to turn out to be sine squared. And then this one, yeah, play with that one. And then this one is this. No, I mean, this is sine and cosine, and you flip things around. It's going to be a basic u sub. This one's power reducing, right? Look, appreciate this. Cosine squared, power reducing formula from last class. Sine squared, power reducing formula from last class. You got to do those. Then once we get everything, right, we got to get theta back to u. And then u back to x. Okay, so see if you can finish that up. What's that? You'll have to use your triangles to get back from theta to u. And this is where your triangle is going to come from. I would do that problem if I were you.
And then what?
Finish it. Huh?
No, after you get it. After you get it from theta to u, then you get u to x.
Yeah, but u to x is easy because all you have to do to solve for x, x is just u plus 1. So whatever you get for u, just add 1 to it. And that's x. Yeah. All right, everyone. Do your homework. I didn't pass around the sign-in sheet today. Sorry. Where's that sheet? Let me have that over here. This. Anyone else need this? All right. You're going to come back a changed person after this